Welcome to Introduction to Quantum Field Theory, Physics 7-70 at the University of Colorado Boulder, Fall 2020. In this first lecture, I will be discussing the notations and conventions used in this course, which are the preliminaries used to understand some of the notations in the rest of the course. The textbook I will be following is called Quantum Field Theory by Mark Stratnitsky, and I will be loosely following that textbook throughout the course. Note, however, that it will deviate both from the orders of the chapters as well as from the content that's presented in the textbook. In particular, I will be using content that's not part of the textbook. If possible, I will be providing references for those contents throughout the lectures where they appear. Throughout the course, I will be using natural units in where I set the speed of light c equal to Planck's quantum h bar equal to Boltzmann constant kb equal to 1. This means that the only unit left is energy, and all the usual units such as time, length, or temperature are expressed in units of energy. I will be using Latin indices to denote three vectors such as a1, a2, a3, and I will be using four vectors such as a mu to write down vectors that involve a zero component, so a time-like component of the vectors. Also, I will be using Einstein's sum convention, which in 3 + 1 dimension just means that whenever an index such as mu is appearing twice, that index is summed over. So a mu then is just a shorthand notation for a mu, g mu, where g mu is the metric tensor, and that is equal to the sum over all the individual components, a0 plus a1, a2, a3. Basically, it just means that the sum symbol over mu is just not written. I will be denoting derivatives such as d by dx by partial x. Similarly, I will be denoting gradients that involve, for instance, the spatial components by di, similar to what I've used for the vectors up here. And I will be using objects such as the Laplacian nabla squared as di, where again, Einstein's sum convention just says sum over all the indices. So Laplacian just stands for dx squared plus dy squared plus dz squared. The metric tensor will be denoted as g mu in this course. I will mainly be talking about Minkowski spacetime, and I will be using a mostly positive sign convention in which the spatial entries of g mu are set to unity and the time-lag component is set to -1. Note, I occasionally might change the number of dimensions that we are studying, discuss non-constant values as entries of the metric tensor, and or change the sign convention. If I do any of these things, I will clearly label these as exceptions, such that normally g mu always stands for this 4x4 matrix that's indicated in equation 1.5. Finally, whenever I write integrals without any limits, these are taken to be improper integrals, such that integral over dx just means that this is an integral from -infinity to +infinity of dx. A similar convention is used for the sum over n, where if I don't write any limits to the sum, this corresponds to the sum n is -infinity to +infinity of an. This concludes the discussion of the notation in this course.